Hey everyone, welcome back to the deep dive. We're diving into something really wild today.
Yeah.
Have you ever heard of a super solid?
I think most people haven't, no. It sounds like something straight out of science fiction.
Right, a solid that can flow without any friction? Like, how is that even possible?
Yeah, exactly. And, well, for a long time, it pretty much was science fiction. It was just a theory. But now scientists have actually created a super solid at room temperature.
Okay, now that's pretty mind-blowing. We have a research paper here detailing this breakthrough, and, well, we're going to break it all down for you.
We will. This is a big deal for a few reasons, but the biggest one is probably the temperature thing. You see, until now, you could only get a super solid at incredibly low temperatures, like close to absolute zero.
As cold as it gets. So making one at room temperature, that's like a complete game changer.
Totally. So, where do we even begin with this?
Let's start with the experiment. How do they actually pull this off?
Okay, so they used a semiconductor. It's a pretty common material in electronics, aluminum gallium arsenide.
Aluminum gallium arsenide. Oh, okay, so nothing too crazy there.
Not yet, but they did something pretty clever to the semiconductor. They engineered it with these microscopic ridges on its surface, like super tiny bumps at almost the atomic scale.
Wait, so these little bumps, they're the secret ingredient?
Exactly. Those ridges are key. They act like tiny little guides, you see? Then they shine a laser on this specially engineered chip. And the light from the laser starts to interact with the electrons in the semiconductor.
Okay, I'm following so far. Light hits electrons. Then what?
Well, when that happens, something really interesting forms. Polaritons. They're these kind of hybrid particles, part light, part matter, and they have some really unique properties.
Half light, half matter. That sounds wild.
It is. So remember those microscopic ridges we talked about? Well, they come into play now. The ridges actually force the polaritons to line up in a specific way, like a very precise repeating pattern, kind of like a crystal.
So that's how they get the solid part of super solid? But
Yeah.
what about the superfluid part? What makes it flow without resistance?
It's all down to quantum mechanics. Those polaritons, because they're in this very specific arrangement, thanks to the ridges, they start behaving as one. They become what we call macroscopically coherent, like a giant synchronized quantum wave. And that wave can move without any friction at all. That's superfluidity in action.
So the laser, it was doing more than just creating the polaritons, right?
Oh, yeah. Think of it like this. The laser isn't just providing energy, it's the conductor of this whole quantum orchestra. By tweaking the properties of the laser, they can control how many polaritons are there, how they interact with each other, and basically force the whole system into this super solid state.
That is so cool. I'm trying to wrap my head around the fact that all this is happening at room temperature.
That's what makes this so groundbreaking. But the question is, why polaritons? Why do they allow for this at room temperature when other particles don't?
Yeah, what's so special about them?
A few things. For starters, they are what we call bosons. This basically means they can do something called Bose-Einstein condensation, which is kind of like when a bunch of particles decide to all hang out in the same quantum state. But here's the kicker. Bosons can do this at much higher temperatures than other particles.
Higher temperatures, like room temperature.
Exactly. And that's thanks to the way polaritons are structured. They have a really strong binding energy between their electron and hole components, which lets them handle the heat. Plus, because they are part light, they have this super tiny, almost light-like mass.
Yeah.
It means they can move really fast and very coherently, like a perfectly synchronized flash mob, but on a microscopic level. And that's what enables the superfluidity. And then, they still have that matter component. That's what lets them interact strongly enough to form that ordered, solid lattice, especially with the help of those little ridges we talked about.
Okay, so these polaritons, they're kind of like this perfect bridge between the quantum world and our world, bringing these crazy quantum phenomena up to room temperature because they're this weird mix of light and matter.
Perfectly put. And they made sure to get solid evidence of this, too. They measured both the repeating pattern of the polaritons, which shows the solid aspect, and the complete absence of friction when they flow, which shows the superfluid aspect. So, no doubt about it.
That's incredible. So this isn't just some cool physics trick, right? This is a major discovery. The first room temperature, super solid, and the first one based on light and matter.
Oh, it is. And this paper really goes into all the hurdles they had to overcome to get there. It wasn't easy. Well, first off, they had to figure out how to precisely control light and matter interacting at the nanoscale. That's no small feat. Those tiny ridges on the semiconductor, they had to engineer those just right. Then there's the laser. They had to carefully calibrate that to get the polaritons to do their thing. And finally, they had to devise ways to actually measure this new state. It's very delicate, this whole super solid thing, not the easiest thing to observe.
Yeah, I can imagine. But now that they have, what does this mean for the future?
Huge potential. I mean, think about it. No more need for those crazy, expensive, energy-sucking cooling systems. This could make studying super solids and using them to build new technologies so much easier.
I bet. Speaking of which, the paper mentioned quantum computing.
Yeah.
How could this change the game there?
Okay, so one of the biggest problems with quantum computers is that they're incredibly fragile. The quantum bits, or qubits, the information carriers, they lose their quantum properties very easily. Like, they get disrupted by the tiniest bit of noise. It's called decoherence.
Right, decoherence. It's like the kryptonite of quantum computing.
Exactly. But imagine this. A super solid lattice. It's incredibly ordered and stable, right? Well, it could potentially act like a shield for the qubits, protecting them from that noise. Plus, the superfluidity could help prevent energy loss in the qubits, which would mean they could hold on to quantum information for much longer. That's crucial for actually doing any complex calculations.
So instead of super cold superconductors, maybe we could have room temperature super solid qubits.
Precisely. And remember, polaritons are part light. Well, that means we could potentially control these qubits with light. It could be a much faster and more efficient way to build a quantum computer and, less need for those giant power-hungry refrigerators.
It sounds like a win-win. But I'm guessing quantum computers are just the tip of the iceberg. What other possibilities are there? I mean, I've heard whispers about super-sensitive sensors.
Oh, absolutely. Supersolids could make incredibly sensitive sensors. Like, imagine a sensor that can detect the tiniest force imaginable, all thanks to the frictionless flow of the superfluid state. That could be a game changer for things like fundamental physics research or even medical diagnostics. Imagine the kind of detail we could pick up.
I'm already getting ahead of myself here, but that's just incredible. What about light-based technologies?
Yeah, photonics. Well, supersolids could be used to create incredibly fast and energy-efficient optical switches. Think about fiber optic communication, for example, or even building entirely new types of lasers. The possibilities are really vast.
Okay, so my head is officially spinning with all this potential, but let's be realistic. When are we actually going to see these super solid devices in our lives?
Well, not tomorrow, unfortunately. There are still some pretty big challenges, like we need to improve the quality of these materials and figure out how to manufacture them on a larger scale. And then there's the control aspect. We need even more precise methods for manipulating these supersolids if we want to really harness their potential.
So more research is needed. That's not surprising. But the future sounds incredibly exciting.
It does. Room temperature supersolids, it's not just some cool physics discovery. It could change everything. Quantum technology, sensing, photonics, and who knows what else we haven't even thought of yet.
So one last thought for everyone listening. Now that we can potentially tap into these crazy quantum states without needing those super low temperatures, what could that mean for the future? What technologies might we see that seem like magic today? It's really mind-blowing to think about. Thanks for joining us on The Deep Dive.
Thanks for having me.
Until next time.